Hi, my name is elhamJahanpeikar. Today I am presenting research on accuracy analysis of supervised and unsupervised machine learning models on breast cancer datasets. This work is also my master's thesis in computer science to graduate from California State University, Northridge. This presentation has 4 sections: introduction, methodology analysis, experimental result discussion, and conclusions and future works. First, introduction. About AI and machine learning. Machine learning is a subfield of artificial intelligence. It is defined as the capability of a machine to imitate intelligent human behavior. AI systems are used to perform complex tasks in a way similar to how humans solve problems. The problem and gap we encountered through reading the available research in machine learning are the absence of producing a comprehensive research on both breast cancer datasets, considerable contradictory results on supervised models, lack of optimization techniques on both datasets, missing unsupervised machine learning models, no deep learning model on one dataset, which is diagnostic dataset. The purpose of this research is to find the best accuracy for selected models from supervised and deep learning models, calculating the performance index in unsupervised models, and with the help of not just one, but multiple optimization techniques, improve the accuracy and other metrics. Next, we have methodology and analysis. We have 2 sections for this part: datasets and analysis. There are 2 datasets available through UCI repository for breast cancer, Wisconsin Original and Wisconsin Diagnostic datasets. I will refer to them as original and diagnostic datasets from now on. For data preprocessing, both datasets were checked and resolved for null values, data type inconsistency, and data scaling. A sample of visualization of the datasets could be seen here, which shows the relation or correlation of the attributes of the datasets. These graphs each illustrate a pair plot of the 2 most correlated features of the datasets: clump thickness and bland chromatin from the original dataset, and concavity mean and concave points mean from the diagnostic dataset. The focus of this research is to select a candidate from each supervised, unsupervised, and deep learning category. The results will be discussed in 2 sections: comparing the model's metrics for original and diagnostic datasets to find if a dataset produces better results, comparing the model's performance, and the metrics will be found after optimization to find any improvement. Logistic regression, k-means clustering, and artificial neural networks are the candidates from each machine learning category. Optimization will be done on each model. All the models and the optimization will be done on both original and diagnostic datasets. For logistic regression, the definition is that it's a supervised classification algorithms in machine learning. It predicts the categorical dependent variables by using a given set of independent variables, and it's used for binary or multi-class classification, and the target variable always needs to be categorical. The logistic regression illustration below shows how, for example, if you need an LR model with 3 features of weather, temperature, humidity, and wind, the model could predict if the weather is sunny or rainy. We are aiming to find the accuracy of such a model and improve this accuracy with optimization techniques. For optimization, for logistic regression are done with hyperparameter tuning, heat maps, VIF, and principal component analysis or PCA. First, hyperparameters. The two hyperparameter tuning methods we use to tune the hyperparameters C in the logistic regression model are stratified k-folds cross validator and grid search CV. Heat maps, as the table shows, illustrates the data in a two-dimensional format in the form of colored maps. Heat maps is about replacing numbers with colors because the human brain understands visuals better than numbers, text, or any written data. VIF, or variance inflation factor. To understand VIF, we just need to know the large value of VIF shows that variable or the feature has correlation with more than one feature. PCA, or principal component analysis, is a technique for reducing the dimensionality of a data set. It gives more information about the data set by summarizing the data set into a concise form, but at the same time, it minimizes the information loss. Through the process, PCAs will be produced. PC1 is the linear combination with the largest possible explained variation, and PC2 is the best of what is left. Generally, PC1 and PC2 hold the most variety of the data set. By the help of the graph, which shows the optimum numbers of PCAs, PC3 was the optimum number for the original data set, and in a separate graph, the optimum number of PCAs was PCA5 for the diagnostic data set. First model is logistic regression on the original data set. Although the metrics which the logistic regression model will be evaluated with are F1 score and accuracy, but the confusion matrices produce promising results, which we show them right here. The confusion matrix shows the number of correct and incorrect predictions. From left to right, the confusion matrix of base model, hyperparameter tuned model, unreduced data set by heat maps and PCA, clearly states that the true positive and false negative, which are crucial diagnosis in breast cancer, have improved by the optimization techniques. Diagnostic data sets, confusion matrices are shown here, and again, all the optimization improved the model prediction. As we can see, the most right matrix has the best values for false positives and false negatives. Next model is k-means clustering. K-means clustering is a model that is an unsupervised machine learning algorithm. It performs the division of objects into clusters that share similarities. The algorithm needs to be told how many clusters it needs to create. And elbow method is a way of finding the optimum value for clusters. And the graph here shows how the similar objects have been placed into similar clusters, as k-means will do. For implementing the k-means, the number of clusters is chosen randomly. The optimum number of centroids or clusters is obtained by elbow method. The performance indexes will be calculated, that here are RAND, adjusted RAND, mutual information, Kalinske and Davis for performance indexes. The higher the index, the better the performance, except for Kalinske and Davis. And we will see in the results section that the Davis index does not improve after optimization by a dimension reduction. And all could be done, and after that, by reducing the data set with heat map technique, we will calculate all these performance indexes again and see for any improvement. The graphs in the top row shows the k-means clusters before optimization. The number of clusters was chosen 5 randomly, and after creating the elbow method, the suggested optimum clusters is 3. On the bottom row, the graphs show the clusters on a reduced dataset by heat maps. In the reduced data set, the elbow graph suggested the number of clusters to be 3 as an optimum number as well. Here, the clusters are shown for the diagnostic data set on the top row before optimization and on the bottom row after optimization by heat map dimension reduction. For this data set, also the optimum number of clusters is suggested to be 3 by elbow graph. The next model is artificial neural network. It is in deep learning category. It's a subset of machine learning. A neural network could have 3 or more layers. It attempts to stimulate the behavior of the human brain. It learns from large amount of data, and a neural network with a single layer can still make some predictions. Additional hidden layers can help to optimize and refine for accuracy. And as the picture illustration here shows, there is an input layer, output layer, and some hidden layers in between that could change from 1 to up to 100 hidden layers for some models. Here are steps toward implementing our ANN model. The data set is balanced, augmented, scaled, and its skewness has been resolved. With the help of Keras from it's an open source deep learning library is utilized for the implementation, and the model training will be performed. For verifying the robustness of our model, we use tenfold cross-validation. The model will be tested after that, and the accuracy is calculated by using 3 optimizers, SGD, ADAM, and RMS probe. And also the model is analyzed by refining hyperparameters, which the optimization happens right here by watching the depth of network, dropout, batch size, epochs, and seeing which number for each of them optimize our accuracy. For depth of network, the data set here was a small data set of 1,880 samples in the original data set. In this case, using the minimum 3 hidden layers of a deep learning network is appropriate to get the best performance. Using more than 3 hidden layers negatively impacts the performance in accuracy because there is not enough data to train the deep learning model. According to the experimental results, no noticeable performance gain was achieved by using dropouts of almost 92% once the number of epochs is 513 or more. The accuracy performance of the new deep learning model is not sensitive to the batch size for the original data set and is sensitive to the batch size for the diagnostic data set. Our implementation found what number of epochs and which optimizer created a stabilized performance in accuracy, which is 858 for the number of epochs. The results of tenfold cross-validation could be seen for each optimizer here. Notice that ADAM optimizer produced a higher average accuracy when tenfold cross-validation was performed on the original dataset. Accuracy score is the number of correct predictions obtained. Loss values are the values indicating the difference from the desired target states. Here we could see the graph for accuracy to epochs relation and loss to epochs relation for the original dataset for each optimizer. Clearly, the SGD optimizer has the highest accuracy relation to epochs, but ADAM reaches better accuracy faster. ADAM optimizer shows less loss compared to the other optimizers for different numbers of epochs. The ROC curve shows the true positive rate to false positive rate or sensitivity over specificity. 0.8 to 0.9 is considered excellent, and more than 0.9 is considered outstanding, which here we see outstanding area under the graph for original dataset. For the diagnostic dataset, tenfold cross-validation produced better average accuracy with SGD optimizer than the ADAM, which was the best performer on the original dataset. For the diagnostic data set, the accuracy and loss relation to the number of epochs, the winner optimizer is the RMS prop, which produces better accuracy and less loss for different numbers of epochs. For the diagnostic data set, both SGD and RMS prop kept the same ROC as for the original data set, which is like 0.99, but Adam Optimizer dropped its score from 0.99 on the original data set to 0.97 in diagnostic data set, which is considered a poorer performance. Here's the experimental results and discussion section. There are 3 tables which summarize all the findings and results of the 3 models for both original and diagnostic data sets. And then we will announce the winner data set and the model in the term of accuracy. This table illustrates from top to bottom the F1 score and the accuracy for the base model after hyperparameter tuning, after dimension reduction with heat map, after PCA application, or after the combination of hyperparameter tuning and PCA application here for the original data set. The next column is for diagnostic dataset. For logistic regression models, the better F1 score belongs to the original dataset before optimization and to the diagnostic dataset after optimization. The accuracy consistently belongs to the original dataset before and after optimization. K-means clustering performance indexes have been summarized in this table. The only difference here is the last 2 index values are the smaller the better. All the performance indexes improved after dataset reduction by heat map, which was the optimization for K-means clustering. But the last index, which is Davis-Baldwin, did not improve after optimization. Artificial neural networks accuracy and loss is shown in this table, which indicates that the original dataset produced the best accuracy with the Adam optimizer and the lowest loss with the SGD optimizer. The tenfold cross-validation accuracy also belongs to the original dataset. The last section of this research is the conclusions on future works. Diagnostic dataset only performs superior in giving the best F1 score, and the rest of the metrics and performance indexes before and after optimization for all 3 models of logistic regression, K-means, and ANN belongs to the original dataset. Therefore, the original dataset is the winner of this research. The ANN model gave the best accuracy score of 99.29%, which outperformed the logistic regression with the best accuracy score of 98%. Therefore, the ANN model is the winner of this research. The future work could be all about these improvements, but not limited to working with different numbers of PCAs, selecting various features of the dataset from the heat map, incorporating the result of the VIF, which in this research could not be useful as it drastically eliminated the features from the original dataset. More data preprocessing like dataset augmentation and label balancing for the logistic regression and the K-means clustering could be considered as future work as well. By saying this, I would like to thank you for listening to this presentation.